Hi, all. Back for another round of physics, I see. And, well, let's get at it. I just decided that we'd do a couple more example problems just to get an idea about energies again. So, up here on the screen, I have the next problem for you. Consider the system shown in the figure with M and M. So, we have a big mass and a little mass M. The rope and pulley have negligible mass, and the pulley is frictionless. In other words, these are what we would call ideal. So, we're dealing with ideal pulley and rope and all that kind of stuff. The coefficient of kinetic friction between the block and surface is, excuse me, copy and paste error, mu. We'll say mu k. So I apologize. Apparently, it doesn't like when I copy and paste from Microsoft Word some of those Greek letters. So the coefficient of kinetic friction between the block and the surface is mu k. In other words, okay, well, we've got to worry about friction here. And there we go. The blocks are released from rest. Use energy methods to calculate the speed of block M after it has descended a distance h. Oh, the M block. Okay, I see. Okay. Whew, cool. Well, we've already done this using forces, so we just decided that we'd go back and try to do it with energy. Again, a lot of addressing the same ideas with a different physical concept. So to start off with, I guess we better sit down and we better ask ourselves, well, what's the system? What's a good choice of system? What's a good choice of surroundings? Okay. In my case, I'm going to choose the system as block big M, block little m, and I'll put the Earth in here. So the inclusion of the Earth in particular means that I plan on using gravitational potential energies rather than work, or at least the work of the Earth. Here in the surroundings, I'm going to leave it as the surface. Surface. And the idea is because mainly due to the idea that the frictional force will cause an increase in thermal energy. So this frictional force will cause an increase in thermal energy of the system, and we haven't talked about that yet. So I think the best idea is to put the surface into the surroundings because then we know how to deal with its interaction with the system. Okay. So the initial state, we'll say just released. And we'll put the final state as fallen distance h. H. And you should ask yourself, how many steps is this problem? That's not a half bad idea to ask yourself. And I would say there's probably, if you really want to get down into it, there's probably 2 steps, but I imagine that you'll probably just do it in one. So we'll see where the second step comes in, but let's go ahead and apply our energy principle. So work is equal to the change in energy of the system. Okay, everything's all fine and dandy there. And in this case, we notice, okay, well, we do have an interaction between our system and surroundings. The surface acts on mass M. And so we do indeed have some work done on it now. So maybe I should look at mass M real fast, and it's going to slide in this direction as the mass little m slides downwards. That means if I think about the force acting on mass M, so here's mass M for a moment, the frictional force should act in the negative x direction. So my frictional force will act in the negative x direction here. At the same time, the displacement of my box is in the positive x direction. And so the work is going to end up being negative. Okay? So in this case, I'll put negative, we'll have our frictional force, FFR, times into my displacement, my delta x. And this will equal the change in, we should ask ourselves, what energies do we have available here? Good. We have the kinetic energy, and we have the gravitational potential energy. let's go ahead and substitute in definitions now. We've got frictional forces, and the frictional force is simply the normal force times, times mu, and I'll drop the subscript, but this should be the coefficient of kinetic friction, so I'll just leave that as mu. Now delta x, if little m falls a distance h, what should delta x also be? Should be h. Now that seems a little weird, right? We said the displacement in the x direction, but the distance the distance of that displacement is also h. So we'll put h here. Over here, we have ke final minus the initial plus the final minus the initial. Let's go ahead and substitute in our definitions for energy. So we have 1/2 m, and here we got to be careful. We have kinetic energy associated with the big M and the little m. And because we're dealing with an ideal rope, as you've already seen in the picture, we can say that those two speeds should be the same. So I'll write this as the kinetic energy. There we go. Right, if I distribute that out, I would get the kinetic energy of the little mass, the kinetic energy of the large mass. Well, oh goody goody. This starts from rest, so this one's 0. BC V naught equals 0. Okay. Now the other question, let's go ahead and let's set our x-axis at the final location, the final height. In other words, let's go ahead and say that this is the final height h, or the initial height, I should say. And so in the final state, we will say that the height is 0. So what I'll do here is I'll cancel this one out, and I'll say because y equals 0. When I do that, okay, well then the last thing I have is minus my initial. This would be mgh. And I should ask, why don't I have anything about big M in the gravitational potential energy? Because big M rests on the surface. It doesn't actually change height. Okay, so we included little m in the kinetic energy, but we don't need to include big M here in the gravitational potential. Okay. Well, let's go ahead. Since I have a flat surface, how does the normal force acting on big M compare to the gravitational force? They're the same. Good. I mean, you can see that if I look at all the forces acting on big M for a moment, I've got the surface, the normal force acting upwards. I've got the frictional force going backwards, Fr. Okay. I've got the gravitational force going down, Fg. Okay. And incidentally, this is if I change my system. This is if I just consider for a second the big mass. Okay. Okay. Now, you should probably do that in your exam. Course, you should probably say F net equals MA. And you say Y direction R. And then you say, I'll give this to you. You can probably skip a line. You can say Fn minus Fg is equal to 0. Therefore, Fn is equal to Mg. So over here, we'll take that result. And that's why I said, it's like 2 steps. This is really the thing you need for step 1. And you do this extra side step just to get the normal force. So I have mg mu h. And last but not least, what I really want to do is get v. I want to get this by itself, the v squared by itself. So I'll shift everything over. I'll move this entire term over to this side. And I will, oh, excuse me. You should yell at me. Excuse me, I got overzealous there. This should not be lowercase m. This should be uppercase M. There we go. Now we're okay. I'll go ahead and move this term over to the other side. And so I'll pull the common term. I've got GH parenthesis M minus mu big M equals 1/2 little m plus big M V squared. And now I get V by itself. I get 2GH little m minus mu big M all divided by little m plus big M equals V. Of course, that whole thing should be square rooted. There we go. And there's our answer. Da da da. Oops. Da 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 da. Yeah da 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 da. Yeah da da da. Okay. And that's it. Now, of course, you can see if you set something like, well, there's a couple of nice little sanity things to look in here. So, for example, one of the things is if the frictional force is 0, or in other words, if mu k is equal to 0, you notice that there is, or say, more energy available to go into the kinetic energy, right? This term disappears, and so then V will actually increase, which is what you expect. If the frictional force were absent, then V should be higher. Alternatively, you could say, for example, there's another really cutesy safeguard in here. You notice that the term in parentheses, which my cursor's kind of hovering around right now, that term in parentheses, if mu times big M is greater than little m, you'll notice that this term ends up being negative. And of course, you can't take the negative of a square root. So what does that physically mean? What does it physically mean if mu m is greater than little m? And here's what it is. It's that the frictional force acting on big M is sufficient to keep little m hanging. Just hangs there. It won't start sliding. And so that's actually safeguard. There's a safeguard built into this equation. Okay. Good. Well, let me pause here. Let's clear the plate, and I'll clear the plate real fast, and then I'll set up the next problem, and we'll go at it again. Okay, welcome back. Well, let's go at another problem here, and this is actually a 4-parter, but it was so bulky on the screen that I decided to only give you a single part at a time, and then we'll go through and do all 4 parts. So here's the first part. If 43 horsepower HP, so I'll say HP horsepower, so if 43 horsepower is required to drive a 2,650 kilogram automobile at 62.7 kilometers per hour on a level road, what is the total retarding force due to friction, air resistance, etc., etc.? Yep. Good. Let you read that again. Well, one of the first things that we actually have to sit down and ask ourselves is, what the heck is this power business? And you basically know the underlying features of it, but it's not only when you're thinking about physics or when you're thinking about practical applications. One of the things that you're interested in, for example, if you're looking at a battery, there we go. Always a good thing to have some sort of example. If you're looking at a battery, one of the things that you're interested in is how much energy is actually stored in one of these suckers. That's number one. But something else almost as important as how much energy can be stored in this would also be how quickly can the energy be pulled out of it. In other words, it's not only how much energy that's in there that's important, but also how quickly it can be withdrawn. Okay? So there's a time aspect to it. That time aspect is expressed in the physical term or physical quantity called power. Let me kind of give you an idea. Well, first of all, power is defined as energy per unit time. Okay. So how much energy in a given amount of time? So for example, power plants. Again, they are not, of course, you're interested in how much energy they can deliver, but it also has to be delivered in a timely manner. So power plants are usually rated not on their energy output, but rather how much energy per second they can deliver. So, a power plant that can deliver, I don't know, 100 million megatons would be great, but if it takes them a billion years to deliver it, then it's not going to be very useful. Okay. So power is sometimes more useful than just knowing the energy. Well, let's see. The units of this, you can see the units of energy are joules, and time is seconds. Okay, so power is in joules per second. We have a different name for this, which you're probably familiar with, is a watt. So capital W, A-T-T. Of course, the abbreviation is just usually the capital W. So immediately you can see where you're going to get yourself in trouble. If you're using capital W, this is also the symbol used for work. Okay, so you just got to be careful. You have to realize what the context is. There's no way around it. Okay. Now, because power is somewhat like energy, we can write some equations that also deal with power. So for example, if I take your work equation, I said work is equal to a change in energy of the system. Well, let me put in the definition. This is the relationship equation. Let me put in the definition of work. And the most formal definition would be the integral of F dotted into dr. Okay? Nothing fancy, just doing the definition of work. Now here's where we'll do something fancy. Two things. First of all, I'm going to multiply this side by 1. Okay. And how I'm going to do that is I'm going to do the force times, we'll put dr dt times dt equals the change in energy of my system. Now what we can do, I haven't done anything fancy yet, just rewriting this. But now I'm going to use this idea of power. Okay? And what I do is I'm going to take a derivative, a time derivative of both sides. So I'll end up with d dt here. And maybe what I should do is, let's move this a little bit over just so that we can, there we are. And I'll put d dt over here. Well, the right-hand side, the change in energy per unit time, that is what we have defined as being power. That's what we have right up here. So let's go ahead and put that in down here. This is just the power. Over on this side, you notice we've got some pretty cool things going on here. First of all, dr dt, that's known as the velocity. So we have the integral of f dotted into our velocity, dt, say d dt. Now here's where we're going to use some ideas about the problem. One of the things, if we go back, right here, although it's not explicitly stated, implicitly, it looks like the speed is constant. And if the speed is constant, presumably the force is also constant since we're dealing with friction, air resistance, etc. That tends to be proportional to the speed, or the speed squared, or some, if the speed's constant, then the force from air resistance is going to be constant. And now we see, hey, we can apply the, is it the fundamental theorem of calculus? You have to double check me on that. I have a derivative, and it's the same thing as not the integrand, but the integral. And so those two undo each other. And so I'm left with something that says, so long as my force and my speed do not vary in time, maybe I should say my velocity, I can write this. Force dotted into my velocity is equal to my power. There we go. And so we are home free. We have now got the solution to the problem. We have F dot V is equal to power. Let's go ahead. We're after this guy. Presumably, F is parallel to V. Okay. And so we have something that says, I'll put retarding times V is equal to power. So last but not least, we have our retarding force is equal to our power divided by our speed. Sub in the values. Now, one thing I should mention, 1 horsepower is about 745.7 watts. And I believe, I'd have to double check, but the horsepower is a unit that we generally use for cars. And I believe it's because that's, what cars replaced. So back in the day when you were actually replacing horses with cars, to give people an idea about how powerful or how much power a car had, you quoted in terms of horses. So, a Model A might have had 10 horsepower. And that was something that people could connect to. I know what 10 horses can pull in terms of a stagecoach, in terms of, heavy masses or whatnot. So it gave people something to latch onto, some sense of familiarity as they went from horses into cars. Now, it's just a holdover since then, to the best of my understanding. So 1 horsepower is 745 watts. In other words, 1 horsepower can power, about 20 40-watt light bulbs. Not bad. Well, let's go ahead and substitute in our numbers since there's nothing more to do here. So we have 43 horsepower, and we have to multiply by our 745.7. That's just a unit conversion to get it into the appropriate SI unit. Here we have 62.7, and that's in kilometers per hour. So to get into meters per second, we end up dividing by this factor of 3.6. So surely you have paused the video by now and you have run the numbers. I got something like 1841 newtons. Again, okay, well, here we go. For a car to drive, just coasting along the road, 43 horsepower, that means it's 1,841 newtons of force acting against it via friction, air resistance, etc., etc. Good? Not like you can actually say that it's bad because, well, I can't hear you. So what we'll do, let's go ahead. I'm going to clear the table off. That's not to mean to say I don't care or I'm not listening. It's just that I can't hear you right now. You're probably screaming at the screen saying, "No, Greg, don't erase that." So I'm going to leave this in here, and let's complete that line just because having that weird looking box, I don't like it. And we'll take this one and we'll move it up here. So we'll save those 2 results just in case they might come in handy later. Okay, well, let's move on to the second question then. And after the wonderful magic of, well, whatever, world of Disney, we have our second part up here. So here's the next question. What power is necessary to drive the same car at the same speed up a 16.9% grade hill? A hill rising 16.9 meters vertically and 100-meter horizontal distance. Oh, okay. Well, the first thing we better do, let's go ahead and draw a triangle to get an idea. So what are we talking about here? We're talking about 16.9 meters for 100 meters. You say, well, shoot. Guess that means that I can probably find the angle of that hill. Let's go ahead and do that. Let's go ahead and just find the angle of the hill real fast. Of course, you look at it, you say, I know this. This is a tangent of theta is equal to opposite over adjacent. And so I get something that says theta is equal to the inverse tangent of 16.9 over 100. Theta is equal to, I have 9.59 degrees. Now you should probably sit there and pause and ask yourself, why in Sam Hill did Greg even go through that right now? Why is Greg going through and putting this triangle in? And hopefully you're already planning the solution out in your head. You realize that if the car is going up the hill, so we talked about the frictional force acting on it from air resistance and everything else. But if it's going up the hill, now we're going to introduce another force acting on the car. And so you would expect that if we're introducing another force acting up on the car and it's traveling at the same speed, you'll hopefully notice that the power provided by the engine better increase. Okay? In fact, here, let's go ahead and draw a car on this slope. There you go. Okay. And let's take the system as being the car. We'll take the surroundings as being the road and earth. Okay? Good. So now previously we'd taken care of the effects of the road, and really the issue is we need to worry about the earth. So if I do my free body diagram, we have, let's say, here's Fg, the gravitational force, and assuming the car is trying to go up the slope, we have the frictional force, air resistance. I guess I'll call it the retarding force. I'll just call it R. Okay, slowing it down. So now if we think about a perpendicular, of course the retarding force is going to be directly opposite the motion. And so if I think about our perpendicular, what we really need is the component of gravity. We need the component of gravity pointing down the hill. That component will allow us to finally calculate the power necessary. So I think we have everything we need. Of course, you've done this problem so much by now, you know that this is Fg sine of theta. This angle ends up being theta. This is the opposite component. Boom, Fg sine of theta. So now we're going to go back and use our handy-dandy equation that we derived earlier. We say F dot V is equal to the power. Well, in this case, we've got two forces. We've got the retarding force. Got a retarding force. And we've got the gravitational force. Well, let's go ahead. We want the components of these forces parallel to the velocity. Remember, that's what the dot product does. It will identify components parallel to another vector. Okay. Now, in this case, I don't have the vector expressions for the retarding force and the force of gravity. I could get them if I wanted to. That's not the easiest way. In this case, the easiest way is to just simply find the components parallel to the surface of the road. So FR, no problem. That's already there. So this one, we're looking now at parallel to surface. We're looking at the components that are parallel to the surface. That's parallel to V. So that was the entire retarding force. We'll put plus Fg sine of theta. Okay, times V. That will equal my power. Okay. Well, let's go ahead. We've gone as far as we can. We've got everything that we need. We have the slope of the surface. We have this from the previous problem. Let's substitute everything in. So you get 1841 plus, and here we have the, oh yes, in the previous part, I believe we said that it was 2650. 2650 times 9.8 times sine of, now we have our angle, 9.59 degrees. And of course, our speed again, 62.7 divided by 3.6. That's our power. Good? Run the numbers. We run the numbers, and I got something that said, okay, well, you just need to provide a measly 1.07 times 10 to the 5th watts. That's what I got for the power. What does this end up being? If you convert this back to horsepower, just for reference, this is 144 horsepower. And there is our answer right here. Now, I'd have to double check, but I think that's still doable for a standard car. I would have to go and check and see what, common horsepowers are. Okay. But I think even just a regular car should be able to do this. 16.9%, that's fairly steep, but I believe a regular car should be able to do this. Okay. Good. Well, let's go ahead. Let me get the third problem queued up here. And we're back. Now, I've got the third part of the problem up here. You see, what power is necessary to drive the car down a 3% grade? Okay. Now, I didn't actually delete everything. I did delete some work from the previous problem, but you see that I still have some of this up. And essentially, the problem hasn't really changed that much. I mean, the only thing that's changed is really now instead of going uphill, I'm going downhill, right? So the idea being, okay, here's my car. And rather than me going uphill, I'm now going downhill. So if I think about my free body diagram again, I've got my gravitational force now going downwards, Fg. And now my retarding force is actually heading up this way, Fr. Okay. Again, thinking about perpendicular to the surface, something like this. And we see that, okay, well, this is angle theta now, theta, which we've changed. It's now 3 degrees. We hopefully see, if you can see, if I look back at what I had down here, what should I change about this line that I have down here? Yeah, remember I went from vectors to this line. I went from vectors and I went to scalars after that, and parallel to the surface. So I'm going to write something. I'm going to stop right here. I'm going to write my retarding force, R, And here's the kicker. I'll put minus the gravitational force Fg sine of theta. In other words, now instead of them going in the same direction where I would have a plus sign, now I have a minus. And that would be equal to my power. Of course, at this point, now we're home free. Let's go ahead and substitute in our numbers. You got 26, and you can pause the video and finish this off. And here, remember, I did 3. And what did I get? Oh, excuse me. I forgot to, you should yell at me. I forgot to multiply by the speed there. There should be a speed in here, phi. Right, don't forget that lovely 62.7 divided by 3.6. You do that old rigmarole, I got something like 8,374 watts. Again, for reference, this is about 11 horsepower. So yes, even going down the road, if you're going downhill, the 3% grade, you still have to be hitting the gas ever so slightly. You have to, you have to be hitting the gas ever so slightly just to get the engine to provide that extra energy. Cool. Well, the last part, go ahead and do that. Okay, so we have the last question up. And again, it comes down, it's, oops, excuse me. We'll go ahead. Okay, so now we have the last question up. Let's go ahead and get rid of that. And I'm going to keep this side again because the last question is, down what grade would the car coast at 62.7 kilometers per hour? Okay, at this point, you've got all the material. I think you can hack this out yourself. You say, well, shoot. If it's coasting, in other words, I want to have P is equal to 0. My car has to do nothing. Okay? But it's a constant speed. So I'm trying to find the angle of the hill at which the energy removed from the system is, the energy invested in the system by the gravitational force is removed by the retarding force. In other words, if I think about my equation I have down here again, I'm thinking I want to find where my retarding force and my gravitational force balance, right? So no power, this is constant. So I'm trying to find a angle where the the retarding force is equal to Fg sine of theta. You got it. Of course, we found this from the first part, 1841 divided by the 2650 times the 9.8. Better do an inverse sign here. Good. And we run the numbers. I got something like theta is equal to 4.07 degrees. So if your slope is angled at 4.07 degrees or greater, then your car, well, if it's at 4.07 degrees, then you do not have to hit the gas at all in order to coast at this speed. You just let off the gas and it just goes. Okay. If it's greater than that, actually you'll need to ride the brakes a little bit. Right? If the angle's greater than this, that means that you'll actually go faster. Okay? The component of the gravitational force down the slope will be larger than the retarding force, and so it'll actually start dumping energy into your system. Okay? Or converse, yeah, that's what I'll leave it there. Next problem. See you in a second. Well, we're back, and this problem, partially it deals with energy, but partially I also wanted to use it to help highlight the relationship between potential energies and forces. So here's the shtick. A certain spring is found not to obey Hooke's law. it exerts a restoring force of blah if it is stretched or compressed. So you see a negative 11x to the sixth minus 50x to the fifth. The mass of the spring is negligible. And the question I have for you, first off, is can we calculate the potential energy as a function of x? So that's our first step. Now, perhaps even the other thing that we should probably double check is to make sure, well, first of all, we should check to see if this force is actually conservative. So how do we do that? First thing we ought to do is let's go to the definition of work. So work is equal to F dot dx. Well, excuse me, maybe I should do it. F dot dr, the most general expression. Okay. And in this case, we're assuming one-dimensional. We've given an x. And so what I'll do is I'll just say, okay, well, this is, I'll label it as f of x dx. Okay. Well, let's go ahead and we stretch it from some x naught position to x final position. Okay. And let's see, what do we do here? Oh, yes. So let's go ahead and we'll plug this in. Negative 11 x to the sixth minus 50 x to the fifth dx. We're going from x naught to x final. Good? Okay. So again, we're asking ourselves the derivative of what function, I'll call it g of x here, would give me negative 11x to the sixth. You can tell I'm just looking at the first term here. And hopefully you see, well, shoot, g of x should just simply be negative 11 over 7x to the seventh. Right? Okay. Yeah, you take a derivative, take the power down, lower it by 1. And similar, you can see, okay, well, how about this one? What the derivative of what function, which I'll call h of x here, so the derivative of what function will give me negative 50x to the fifth. Hopefully see the same song and dance applies. H of x will simply be equal to negative 50 divided by 6 x to the sixth. Cool. Well, you've done it. You have now done the integral. We have negative 11 over 7 x to the seventh minus 50 over 6 x to the sixth. There is, I'll say from x naught to x final. That would be the work done by the spring. So this weird, funky spring. So maybe one of the other things that we should check on this is to see if it's path dependent or path independent. So we've got our expression for how to calculate the work here. Okay, that's, of course, that's deserving of a box. And one of the things that I'm curious about immediately is it path dependent or path independent? So how do I test that? How would I double check that? I think the easiest way to check it is, let's say I stretch it from x naught to some intermediate point, and then from that intermediate point to x final. Okay? In other words, I'm going to check to see, I'll start with this. Oops, excuse me. If it's truly path independent, so I should be able to say work is equal to work. That's first of all. And if it's truly path independent, I should be able to do this. So I'm just writing out the equation here. X to the sixth. I should be able to do this from x naught to x final. In other words, I just do it in one step. Okay. And the question, if it's truly path independent, then I should be able to do this as well. what I'm going to do is I'm going to put in some intermediate step. Say 56 x to the 6th. I'll go from x naught to x1. And then I'll do it again. Negative 11 over 7 x to the 7th minus 50 over 6 x to the 6th from x1 to x final. And yeah, so what I say, x1 is like this intermediate step. Well, shoot, you can see here, if I substitute an x final, and how you evaluate these things is final minus initial. So I do negative 11 over 7 x final to the 7th minus 50 over 6 x final to the 6th. So minus, now here it comes, you got to be careful, negative 11 over 7 x naught to the 7th minus 50 over 6 x naught to the 6th. So just substituting in. And the idea is, does this equal question mark? So let's go ahead and take a look-see here. So we see I've got, now we just go through and start doing this cancellation game. I've got this one and this one. So those cancel. And these cancel as well. Now I have a minus minus x naught and a minus minus, so this one. And we see that I'll underline that whole thing, this matches this. So those go out. One goes out and this one goes out. And then lastly, we take a look and we have, underline in a different color, negative 11 sevenths x1 to the 7th, and then we have the positive one. Those cancel. Go this way. And again, same thing, a negative, and we have a positive. So those cancel. And we get an expression that says 0 equals, and we'll put check mark 0. So evidently, in this case, this equation apparently is path independent. In other words, it doesn't matter where I stop along the way. I can introduce some midway point in 1D at least, where it doesn't matter where I stop. That should be helpful and comforting to know. Okay, well, it's always good to check. Well, that means that we're pretty much done here. Okay. If this is truly a conservative force, then the last thing we do is we recognize for conservative forces, the work is equal to the negative potential. In other words, if I want the potential energy here, if I want an expression for the potential energy, that would just be 11 over 7 x to the 7th plus 50 over 6 x to the 6th. Cool. Nice. And of course, notice that the delta is coming in from this x final minus x naught. We're good to go. Sweet. So let's go ahead and we'll keep that in our back pocket. I've got a pocket full of potential energy. Doesn't have quite the same ring to it. Okay, so let's just get rid of all that. And the next thing we'll do is let's move this over here. Well, last thing, why don't we get a flavor of how to use this? Let's say that there's a mass. So now that we have this, I mean, pretty straightforward, but let's go ahead. Let's say that we have an object attached to this spring that has a mass of 6.4 kilograms. And the spring is pulled to a distance, we'll say the starting distance for the spring, x naught is 2.3 meters. 3 meters. I'll say from, how about not for? How about if I say from equilibrium? Okay. And the question then becomes, what is speed? We'll put v, the x direction, at x final equals 0.3 meters, question mark. So in other words, you have a mass, so you have this spring right here, and you have the mass attached to it, we'll call it m, and it's stretched a distance of 2.3 meters. This is the initial state, of course. The final state being where I have the spring and it's stretched 0.3 meters. There we go. Okay. Good. Well, let's go at it. Of course, you've already, this is just a practice using the potential energy, just some random potential energy now. We'll call our system the box and spring. We'll call our surroundings, I guess you could say the earth and the surface. Okay. Initial and final, you've already got. We've drawn pictures for that. Okay. And so we go to our idea. The work is equal to the change in energy of the system. Of course, over here we notice the Earth does no work on the system, right? The gravitational force is downwards, Fg, whereas the displacement is either to the left or to the right. In other words, Fg, let's say Fg, I'll call it a vector, is perpendicular to the displacement and therefore does no work. Similarly, the surface exerts a force Fn going upwards, and that's also perpendicular. I'll say Fn is also perpendicular to delta R. And so these two together means that work is equal to 0. It's a closed system. Hopefully you're rocking and rolling at this point. We've got a closed system. We'll say 0. What forms of energy exist? We have our kinetic energy and our spring potential energy. Put spring here. We go at it. Because this is 0, we'll say that means that our initial must equal our final. We plug in our values. Here, we're from rest, so we'll say 0. And then we have this old rigmarole. So what we'd have to do is we'd have to put in 11 sevenths times 2.3 sevenths. So this is a lot of energy, right? Plus 50 over 6 times 2.3 to the sixth. This whole thing would have to be equal to 1/2 times 1/2 mv squared. So we got 6.4. Pretty heavy box, squared, plus, and then we have this rigmarole all over again, 0.3 to the 7th, plus 56th times 0.3 to the 6th. Of course, these numbers are so stinking small, it's essentially 0. Okay, so go ahead, plug it in your calculator. So we run it. And I got something like, over here, I got something like 1768 equals 1/2 times 6.4 v squared plus, and like I said, this number is essentially 0. I got 0064. So compared to 1768, this is like nothing. Okay. Well, you can finish this off. Alpha, let's see here. Go ahead and do this. So I stored everything in my calculator so that even though it's close to 0, I can still do it. Just 2 divided by 6.4. So I get something like, okay, well, this is 552.7 equals v squared. Or, of course, if I take a square root, I get something like 23.5 meters per second equals v. And again, there's the answer I came up with. Okay. Well, very good. You've been pretty attentive. I think we'll leave it there for right now. Maybe one more video just to give you a flavor of how interesting some of these problems can get. Thanks for your attention. I'll see you next time.